level curves. So we can look at it in terms of uh, xy is equal to c, or we could say that y is equal to c over x. Okay, so basically, and let me see how I wrote that. Okay, so if we take a look at this, um, you have basically two situations can come out. Okay, so in this, you can get if if c is equal to 0. If c is equal to 0, you're just going to get basically you're going to get a series of points that either are going to be x comma 0 or 0 comma y. Okay, so it's going to be points along these. Since it's x0, that represents the x-axis. If it's 0y, that represents the y-axis. Okay, now if c is anything else other than 0, okay, now in the problem I say that it's in the solution it says it's hyperbolous, but if you say that it's a family of rational equations, family of rational equations with uh, the x and y axis as asymptotes. That would be saying the exact same thing. Okay. So again, let me just explain this again. So basically, if we let c be 0, then the only way that c can be 0 is that either x is 0 or y is 0. So if y is 0, it creates a set of points of x comma 0, which is just the x-axis. If x is 0, it creates a set of points that 0 comma y, which is the y-axis. Now, c takes on any other value other than 0, then you're going to have a family of rational functions with the x and y axis as the asymptotes. Any questions there? Okay. The part D is to find the boundary, find the boundary of the function's domain. So if we look at that, okay, so if we find the boundaries of the for the domain, so for that particular issue, if we say that xy is equal to 0, all right, so your options would be that x is 0 or y is 0. Okay, but if you look at the second piece of this, x can't be 0, y can't be 0, because essentially what you have created here, these are the asymptotes. Okay, and if you think about asymptotes, they're not boundaries, so they're not enclosing anything. So since these really are not enclosing anything, there are no boundary points. Okay, so they are just basically values that the function cannot take on, but they don't necessarily enclose the region. Okay. All right. Part E, determine if the domain is open, open or closed. Okay. So if you look at it in terms of, uh, if you look at the two conditions of the domain, let me go back. So if you look at the conditions when C is equal to when C is equal to 0, we have this. Okay. So in this case, it does create a it does create a closed region. But on the second piece, if you look at this, basically, if we are looking at the graphs of this, it's going to be the family of functions that are going to look like this, going this way, family of functions like this way, and then it's going to switch in the quadrants based on if C is positive or negative. So if C is positive, it's going to deal with just these. If C is negative, it's going to deal with these. Well, if you think about it, are these curves ever going to be bounded? No, because they're just going to expand out, expand out, expand out, expand out. So for this piece, it would be open, but for this piece, it would be closed. So in part E, we would say that they're both open and closed. Okay. And then part F, is it bounded or unbounded? Well, if you think about it, if you look at this region expanding out, it's not able to be encompassed in a circle. So it keeps expanding out. So it makes it unbounded. Okay. Any other questions? All right. Okay. So let's see. We got through everything in there. So what we're going to do is to move into our next section, um, which is going to be focusing on dealing with derivatives. Okay. Any other questions before we move on?
On the answers for the homework functions of several variables, it said that you would talk about in class for the other ones. So I don't know if you're gonna go over those
Oh,
more
okay.
later.
So let me see here. Let me pull those up. Put those up real quick because I think that was dealing with the topical curves and the spaces. Okay. So let me look at those and I'll put those answers up real quick. Okay. Let's see. The first one is number 5. Okay. All right. So let's take a look at this. All right. So for question number 5, we're looking at f of xy is equal to y squared. Okay. So if we do the sketch of the, um, we're going to do a sketch of the function, and then we're going to do the, um, the level curves. So if we do a sketch of this function, all right, if you take a look at this, okay, this equation is basically focusing on what two variables?
X and Y?
It won't be X. It's going to be Y in one other variable. Yeah, it's going to be Z, because you have to understand that f of x, xy is the same thing as Z. Okay? So, excuse me. So everything is in terms of Z. All right? Z and Y. So that means that X can take on any values. So if I take a look at this, it means that if I do 1, then I'm basically going to create parabolas along the Y and Z. Okay, so it's going to be up and down. But what's going to happen is that I can expand this along the x-axis. So you're going to have parabolas that are a tube like so that's going to be along the x-axis, but it's going to open up. Okay. Any questions there? All right. So that's part A. And then part B is doing the level curves. Okay. So if I look at that, that means I'm going to push it down into 2 dimensions. So if I push this down into the XY plane, okay, so at z equals 0, I'm just going to get a line that's going to look like this. Okay, when z is 1, I'll get another line that looks like this. Then our next value will be when z is 4, I'll get a line. And then I can do the same thing going back down. So I can get a line here and a line here. So this would represent z is 4, z is 1, z is 0, z is 1, z is 4. Okay, and basically what it's doing is just taking on the different values of y. So if y is 0, that makes z 0. If y is 1, that makes z 1. 1. If y is 2, that makes z 4. If y is negative 1, that makes z 1. If y is negative 2, that makes z 4. So it's just going to create these straight lines. Any questions? Okay, so next, let's look at the next one. All right, and this is for question number 6. In this one, we are doing that f of xy is equal to negative x squared plus y squared. Okay, so if we look at part A, which is going to be the 3-dimensional drawing, okay, so essentially here, if we are going to deal with this, we know it's going to start at the point 0, 0. Okay, now if you think about this, in order for this to work, all right, what do you think I'm going to be dealing with here? If I look in just the XY plane, what do you think I'm going to be dealing with?
Circle?
It's going to be circles. But for this, instead of it going up, it has to go down because of the negative, because it's just going to flip everything over. So we're going to have circles that are going to be created. Okay, so we can look at when z is -1, and we're going to have a circle there created. And as we go down in the values of z, what's going to happen to the circles? So as we go down in the values of z, so z is -4, what's going to happen to the circle? So if we've got z is equal to -1, we've got that negative of x squared plus y squared is equal to -1. So we have x squared plus y squared is equal to 1. So if z is -4, I'm going to have negative of x squared plus y squared equals -4, or x squared plus y squared is equal to 4. So what's happening as z decreases?
The circle is expanding.
Yes, its circle is expanding. So basically, as we increase our values of z, decrease our values of z, the circles are going to get larger and larger and larger. So we'll start off with a circle with the radius of 1, and then it's going to get bigger. So I'm going to open down like so. Okay. And you're going to have this. Okay. So you're just going to have kind of a parabola shape, circular figure opening down. Okay. So next, if you collapse this, okay, into a two-dimensional shape, okay, keep in mind that in order to create this, everything is going to be circles. So if we do the level curves, okay, as a two-dimensionals, so the first one is going to be z is equal to 0. Next, we're going to have a circle with a radius of 1. So that's when z is equal to -1. It can't be +1. It has to be -1. Then we're going to have another circle with a radius of 2. That would be that z is equal to what? So if we've got a radius of -2, a radius of 2, what would be the value of z? Z would have to be -4. You have this. Any questions? Okay. All right, let's look at the next one. And this is problem number 7, I think. So here we've got f of x y is equal to 1 minus the absolute value of y. So if we want to look at the graph of this, okay, keep in mind that as far as this function is concerned, it's void of what variable? It's a void of x, so that means it's going to expand along the x-axis. Now, if we look at this, okay, we're basically looking at the graph of a absolute value function, but it's just going to be, and let me switch colors, it's going to be dealing with only z and y. So this tells me it's going to shift up 1. And since it's negative, it's going to open down. So this is what you're going to have. Now, just keep in mind that, and I'm blocking it off just to hit the axis so I can have kind of a solid figure. Keep in mind that this is going to be parallel with the x-axis, okay? And you're going to have several of these going along, okay? Any questions? All right, and in part B, we're going to look at the level curves, okay? So you don't really care what x is going to be, it's just y. So if y is 0, okay, I'm going to get a level curve here, okay? And what's going to be the value of z if y is 0? If I plug 0 into this, what will I get? Get 1, okay? So next, if y is 1, so if I plug 1 into this function, what's the value of z that I'm going to get?
0.
I'm going to get z is equal to 0. All right. Suppose that y is 2. What z
-1.
value am I going to get?
-1.
Yeah. Okay. So now if I go down, if z is, excuse me, if y is -1, what value will I get?
0.
Okay. And then if y is -2, what value will I get?
-1.
Okay. Now, the reason why it's straight lines, so let's think about it. It's void of x, so that means x can take on any value. Any questions? Okay. All right, so we got 2 more that we're going to talk about real quick. The first one is this, and I think this is going to be problem number 10. So we're dealing with f of x, y, z is equal to, we're dealing with x squared plus y squared plus z squared. Okay, so if I look at this, this is basically going to be dealing with a, and we're going to do level surfaces, so we're saying this is equal to c. So really, this is just the blanket equation for a sphere. So if we do the graph of this, okay, so we're going to have, let's do all this. So we're going to have a circle in terms of y and z of a radius of 1. We can have a circle in terms of uh, x and y. Okay, so we basically, by connecting those, we create a sphere. Okay. Any questions? Okay, and then the last one we have is number 11. So we have f of x, y, z, and this is equal to z minus x squared minus y squared. Okay. So if I take a look at this particular one, okay, so again, I can set this equal to C. Okay, so basically what I end up with is I can look at it in terms of Z is equal to X squared plus Y squared plus C. All right. So the easiest thing what I can do is to start off um, with C equal to 1. Okay. So if I look at it in terms of C equal to 1, okay, so if both X and Y are 0, this is going to be shifted up 1 unit starting here. That's the start off value of the circle. Now, as Z increases, because Z, there's no way that Z is going to decrease. So as Z increases, basically every level that we go up, we're going to create a circle on the XY plane, but it's just going to create a circle in Z equals whatever number that is. So we can get that. So we're going to have this here. And basically it's going to create circles going all the way up, like so. Okay. Any questions? Okay. Any other questions? Okay, so let's move into our next section. In our next section, we are going to be dealing with partial derivatives. All right, so when you take a look at the notes, basically, I kind of give you the limit definition for excuse me, for the partial derivative. So when we're dealing with partial derivatives, we do switch up a little bit different. Okay, so hold on 1 second. Okay, so with partial derivatives, all right, so we have what we refer to kind of our first partials. Okay, so our first partials, so when we do the partial derivatives, we're going to have the partial of the function in respect to whatever variable. Okay, so when you're doing a partial derivative, whatever variable you're taking derivative in respect of, that's the variable. All other variables are considered constants. So you can take the partial of f in respect to x. You do the partial of f in respect to y. You can do the partial of f in respect to z. Okay? Now, we also have what we refer to as our second order partials. Okay, so we've got the partial squared in respect to f of x squared. we've got the partial squared of f in respect to y squared, okay? And then we also have what we call the mixed partials. So we got the partial squared of f in respect to y, then in respect to x. Then we have the partial squared of f in respect to x, then in respect to y. Okay. Now, we don't always use the notation like I've got written here. Sometimes you'll see the notation written as f sub xx, f sub yy, f sub yx, f sub xy. Okay. So this is another way that you see that means that you're going to take the partial derivative. Okay. Any questions? Excuse me. All right. So next we do have what we refer to as the mixed partial derivative theorem, which basically says that if f of x, y, and its partial derivatives are defined throughout an open range, containing a point a, b, and are all continuous at a, b, then we can say that the partial of f in respect to x and y of ab is equal to the partial of f in respect to y then x of ab. Okay, and we'll do an example to show you that the mixed partial theorem does hold, so you don't have to worry about checking both ways. But I'm going to do an example where we do check both ways to show you that, hey, they're going to be equal. All right, so let's take a look at some examples of doing the partial derivative. Okay, all right, so our first example is this. We have f of xy is defined as x squared minus xy plus y squared. Right? So the first thing we're going to do is to find a partial of f in respect to x. Okay, so what this is telling us is that we're going to take the derivative in respect to x. Any other variable is treated as a constant. Okay, so if I take the partial of f in respect to x of the first term, I'm going to end up with 2x. If I take the partial of x in terms of second term, x is your variable, y is your constant, so I'm just going to end up with y. And then if I take the partial in respect to of f in respect to x of the last term, it's going to be 0. Any questions? Okay. All right, the next one, we're going to do the partial of f in respect to y. Okay. So if I do that, all right, so if I take the partial of f in respect to y of this term, I'm going to get what? I'm going to get 0 because x is considered a constant. All right. Then if I take the partial of f in respect to y of the middle term, what will I get?
Negative x.
Okay. And then if I take this partial of f in respect to y of the last term, I'm going to get what?
2y.
And there we go. Okay. Any questions? All right. Let's look at the next example. All right. So if I take a look at the next example, I have f of xy is equal to x cubed plus y over 2 to the 3 halves. Okay. So the first time, I'm going to do the partial of f in respect to x. Right? So if I do the partial of f in respect to x, all right, so if I take the derivative of this, do you have to use the general power rule? So I'm going to have 3 halves times x cubed plus y over 2 to the 1/2 power, okay, times the derivative of the inside. So if I take the derivative of the inside in respect to x, I'm going to end up with just 3x squared. Now, the derivative of y over 2 is going to be what?
0.
It's going to be 0. Okay?
By the way, I think you copied the question wrong. It's gonna be 2 over 3, right? Like the
Oh,
power
so
is
yeah, sorry.
yeah.
Yeah. So that is, my exponent is wrong. So let me fix that, and I'll fix the, so this is 2/3. So all right, so that's going to make this 2/3. Second. So 2/3. Yeah, my pen is acting up again today. And this is going to be negative 1/3. Okay. All right. Okay. All right. Give me a couple of minutes. I'm going to have to restart my iPad because, again, my pen is messing up. So just give me a couple of minutes to do that. All right. Let's see if I can get everything to work correctly now. Can everyone hear me okay? Okay. So let me see if I got my pen working correctly now. All right. So this is going to be 2/3. This is going to be negative 1/3. All right. So if I kind of clean this up, what I'm going to end up with is going to be, oh great, it's still acting stupid. I'm going to get 2x squared I'm going to get 2x squared over x cubed plus y over 2 to the 1/3. And I apologize, this is happening for some reason. Having issues today. All right. And I'll write this a little bit cleaner here in a moment. Okay. All right. Any questions? Okay, so next, still the same problem, but I want to look at the partial of f in respect to y. So if I look at the partial of f in respect to y, again, the 2/3 is going to come down. And then I'm going to be left with the x cubed plus y over 2, and I'm going to raise to the negative 1/3 power. And then I got to take the derivative of the inside, so chain rule. It's chain rule, but it's chain rule in the aspect of how we've done chain rule back in Calc 1 and Calc 2, but it's not going to be the chain rule that we're going to learn in the next section. Okay, so if I take the derivative of the inside, what will that give me?
1/2.
Okay, so we're going to get 1/2 here. So again, I'm just going to want to clean that up a little bit. So if I clean it up a little bit, I'm going to end up with 1 over 3 times let's see here, we're going to have x yeah. All right. It's going to be x cubed plus y over 2 to the 1/3 power. Any questions? Okay. All right. Let's look at the next problem. So if I take a look at this one, the next one is that we've got f of xy is equal to the tangent inverse of y over x. Okay. So if I look at this and I want the partial of f in respect to x, okay. So again, what I'm going to do is I'm going to start off with this, okay, the tangent inverse. So if I do the derivative of tangent inverse, it's going to be 1 over 1 plus, and we got the expression that we're taking the tangent inverse of squared times Now, if I take the derivative of this expression here in terms of x, what would that be? So what's going to be the derivative of y over x in terms of x?
A negative 1 over a squared.
So yeah, so negative y over x squared. Okay, so basically what we're going to do is just try to clean this up a little bit. So this is going to be the same thing as 1 over 1 plus, we're going to have y squared over x squared times negative y over x squared. Okay, so if we multiply this out, okay, we're going to end up with negative y on top. And then for the denominator, we're going to end up with x squared plus y squared. And that will be our derivative. Any questions? Okay, so next, still working with the same function, but we're going to do the partial of f in respect to y. Okay, so still the same thing has to happen is that we got to take the derivative of the dealing with the tangent inverse first. So that's going to be 1 over 1 plus y over x squared times. Okay, now we're going to take the derivative of y over x in respect to y. So we're going to get, yes, 1 over x. Okay, so essentially what we're going to do is to clean this up. So that's going to be 1 over 1 plus y squared over x squared times 1 over x. Okay, so essentially this is going to give us 1 over x plus y squared over x. So I'm going to do one more multiplication of x over x because I don't want the complex fraction. So I'm going to end up with x over x squared plus y squared. Okay. Any questions? Okay, so let's take a look at the next one. So if I take a look at the next problem, I have this. I have f of xy. It's equal to cosine squared of 3x minus y squared. Okay, so I want you guys to do the partial of f in respect to x and then find the partial of f in respect to y. All right, so I'll give you a couple of minutes to see what you come up with on that. So let's see how you did. Let's take a look. So the first one, if you take the partial of f in respect to x, you should have 2 times the cosine of 3x minus y squared times derivative of cosine is going to be negative sine of the angle, which is going to be 3x minus y squared times the derivative of the angle in respect to x should be just 3. So we should end up with a final answer of negative 6 times the cosine of 3x minus y squared times the sine of 3x minus y squared. Okay. Any questions? Okay, so let's take a look at the next one. So if I take the partial with respect to y, I should get starting off 2 cosine of 3x minus y squared, and times, it's still going to be the negative sine of 3x minus y squared. Then we're going to take the derivative of the angle, so that should be negative 2y. Okay. Now, if I clean that up, I should end up with the two negatives are going to make a positive, so I'm going to put the answer on the next page. So we're going to end up with 4y times the cosine of 3x minus y squared times the sine of 3x minus y squared. Okay. Any questions? Okay. All right, so next, let's look at the last example that we have. And it is this. We've got f of x, y is equal to the sum as n equals 0 to infinity of xy to the n. And we're told that the absolute value of xy is less than 1. All right, so in this particular problem, one of the things that we have is that we can't deal with it in this format. So we need to convert it over to something that we can deal with. So if we take a look at the series, what kind of series is it? If you take a look at this series, what kind of series is it? Yes, it's going to be geometric. And the common ratio here is going to be what?
One over one minus xy,
Okay,
right?
so that's going to end up being the sum. Okay, so we can say that f of xy can be defined as 1 over 1 minus x, 1 minus, no, excuse me, 1 over 1 minus xy. I was right the first time. Okay, so this will be our function. Okay. Any questions? Okay, so now that we have the function defined, so we have f of xy is defined as follows, or we can write this as 1 minus xy to the negative 1. And that may be a little bit easier for us to deal with in terms of doing the derivatives. So if I do the partial of f in respect to x, so how's that going to start?
Negative 1 minus hy, the power negative 2.
Okay.
Then multiplying with negative y.
Okay. So this will be the derivative. So if we clean it up and get rid of the negative exponents, we're going to end up with y over 1 minus xy to the second. Any questions? Okay, so now let's do the other partial. So let's do the partial of f in respect to y. Okay, now just keep in mind this is going to start off the exact same way. So it's still going to start off as negative 1 times 1 minus xy raised to the negative 2. Then we're going to take the derivative of the inside. So if we take the derivative of the inside in respect to y, what will we end up with?
Negative x.
Okay, so again, we're going to clean it up and get rid of the negative exponents. So we're going to end up with x over 1 minus xy to the second. Any questions? Okay. All right, so we're going to pause right here for a moment. We're going to take like a 7-minute break. I'm going to try again to restart my iPad and see if I can get it to start cooperating right. And we'll meet back up at 12:10 to finish up class. Okay. right, so let's look at our next example. Okay, so in our next example, we have this. We have that f of x, y, z, and this is going to be equal to x squared plus y squared plus z squared to the negative 1/2. Okay, so the first time what I'm going to do is look at f sub x, which basically means find the partial in respect to x. Okay, so if I find the partial of f in respect to x, I'm going to end up with this. I'm going to have negative 1/2 times x squared plus y squared plus z squared, and it's going to be raised to the negative 3/2 times the root of the inside, which is going to be just 2x. Okay, so if I clean this up, I'm going to end up with negative x times x squared plus y squared plus z squared to the negative 3/2. Okay, any questions there? Okay, next, still the same function, but this time we're going to do the partial in respect to y. Okay, so if I do the partial in respect to y, what's going to come up front?
Negative 1/2.
So we're going to have negative 1/2 times the expression, which is x squared plus y squared plus z squared, and it's going to be raised to the what power?
Negative 3/2.
Okay, and then we're going to multiply it by what?
2y.
Okay. All right, and if we clean this up, we're going to end up with negative y times x squared plus y squared plus z squared to the negative 3/2. Any questions? Okay, next, let's look at the partial with respect to z. So if you look at this, it's going to start off the exact same way as the other two pieces. But we're going to multiply it by what?
By 2z.
Okay.
2z.
So yeah.
Sorry, my
So
bad.
if we do that and clean this up, so we're going to end up with negative z times x squared plus y squared plus z squared to the negative 3/2. Any questions? Okay, so let's look at our next example. Our next example is that we've got f of x, y, z, and this is equal to e to the negative x, y, z. So if we take the partial of f in respect to x, what will we end up with?
Negative e to the power negative x1z.
Okay,
Oh, negative 1z.
so yeah, so you got to have that, and then raised to the negative e raised to the negative xyz. Okay, because you have to understand that as far as it's concerned, this is just one big term. But when you're taking the partial with respect to x, these are constant. So this is derivative. This is just going to be -1, and then you've got to still tack these along. Okay. Any questions? All right. What about partial with respect to y?
Negative xc and e to the power negative x1z.
Okay, good. All right, and then our last partial will be in respect to z. So what will that be?
Negative 1z e to the power negative x1z.
Negative xy raised to the negative xyz. Any questions? All right. Are there any questions about doing the first order partials? Okay, so the next examples are we're going to be doing the second order partials. Okay, so the first problem we're going to have is going to be this. Right, so we've got f of xy, and this is going to be equal to the sine of xy. So in order to do the second order partials, we got to do the first order derivatives first. So we need the partial of f in respect to x. So if we take the partial of f in respect to x, so the derivative of sine is going to be cosine, keep the angle, times the derivative of the angle. So since this is respect to x, we're just going to end up with y. So we're going to end up with y times the cosine of xy. Any questions? Okay. So next, let's find the second order partial in respect to x. So we're going to take the derivative of this in respect to x. Now, let's remember that y is what?
A constant.
It is a constant. So if we take the derivative of this, we're going to have y times derivative of cosine is going to be negative sine. Keep the angle times the derivative of the angle, which is going to be what? And keep in mind I'm taking in respect to x.
Y.
It's going to be y. So we're going to end up with negative y squared times the sine of the angle xy. Any questions? Okay, so we're still not done with the derivatives. I need to go back to the beginning. All right. So now we're going to do our partial in respect to y. All right, so if we do the partial in respect to y, all right, the derivative of sine is still going to be cosine. Keep the angle at xy times the derivative of the angle in respect to y. It's just going to be what?
X.
Okay. So we're going to have x times the cosine of xy. Okay. So now what we're going to do is take the partial of y in respect to y again. Partial of y, and we're just going to do it twice. So we're going to take the derivative of this in respect to y. Now, again, keep in mind that x is going to be a constant. So we're going to have x times derivative of cosine is negative sine. Keep the angle times the derivative of the angle in respect to y is going to be x. So we're going to end up with negative x squared sine of xy. Any questions? Now, the only other thing that we're missing is the mixed partial. Okay? So if we do the mixed partial, we've already done the partial in respect to x. All right, so we said the partial in respect to x is y times the cosine of xy. So now what I'm going to do is to take the derivative of that, but then in respect to y. So now, keeping that in mind, that means that y is now your variable derivative. So in order to take the derivative of this, I'm going to have to use the product rule. So I'm going to say first times derivative of the second, which is going to be negative sine of the angle times derivative of the inside in respect to y, which is going to be x, plus the second times derivative of the first in respect to y, which is 1. So if we clean this up, we're going to end up with a negative xy times the sine of xy plus the cosine of xy. Any questions? Now, in this problem, I am going to show you that by using the partial theorem, we'll get the same derivative. So we did it where it was x first, then y. So now what I'm going to do is to switch it around and do the other and show you that we're still going to get the exact same answer. Okay, so let's take a look at that. Just basically, I just want to show you this. So, but you don't have to do it every time. But I want to show you so you just don't assume that, okay, the theorem is true. Let's look at and to actually show that it is true. Okay, so in this one, we're going to start with the partial of f in respect to y. Well, we said that was equal to x times the cosine of xy. So now what we're going to do is the partial of this of y, then in respect to partial of f in respect to y, now in respect to x. So if I take the partial of this in respect to x, keep in mind that x is the variable. So again, I'm going to have to use a product rule here. So I'm going to do first times derivative of the second, which is going to be negative sine of xy, times the derivative of the angle in respect to x is going to be y, plus the second times the derivative of first, derivative of x in respect to x is just going to be 1. So if I clean this up, I'm going to end up with negative x, y, the sine of xy, plus the cosine of xy, which is the exact same derivative that we just got. Okay. Any questions? Okay, so let's look at our next example. All right, our next example is this. So we've got f of xy is equal to x e to the y plus y plus 1. Okay, so first, let's find the partial of f in respect to x. So what would that be?
Just e to the power y.
Right. Okay, so next, let's do the partial of f in respect to y.
H1 e to the power y plus 1.
So x times e to the y plus 1. Okay, so we've done the first order partial. So now let's do the second order partial in respect to x. What will that give me?
One.
Careful.
0.
Yes, because keep in mind we're taking the derivative of this in respect to x. So let's treat it as a constant. Derivative constant is 0. Okay, so now let's do the second order partial of y. So we're going to take the derivative of this in respect to y. So what should we get? Yes, we're going to get x e to the y. Okay, because the derivative of this is going to be 0. Derivative of this, x is a constant, so it just comes along to the right. Derivative of e to the y is just going to be e to the y. Okay. Any questions? All right, so the only other thing that we're missing is the mixed partial. And for the mixed partial, it doesn't matter how you start it, okay? In the previous problem, we show that you can do it either way. You're going to get the same answer, okay? So you just got to choose one of the ways. You don't have to do both. So if we do the partial of x and in respect to partial of f in respect to x in respect to y. So now I'm going to take the derivative of this in respect to y. And what would that be? Yes, it's just going to be e to the y. And that will be the mixed partial. Any questions? Okay, so now let's take a look at our last example. Okay, so the last example that we have is this. We have that s of xy, so s of xy is equal to the tangent inverse of y over x. All right, so we're going to start with the partial of s in respect to x. So if we start off by taking derivative of the tangent inverse, it's going to be 1 over 1 plus. We're going to square this, so it's going to be y squared over x squared times. Now we're going to take the derivative of this in respect to x. So what would that be?
Negative 1 over a squared.
So negative y over x squared. And we do want to clean this up since we're going to have to do a second derivative. So if we clean this up, we're just going to multiply this out. So we're going to end up with negative y over x squared plus y squared. Okay. Any questions? Okay, so next, let's look at this. Let's do the partial in respect to y. Okay, so if we do the partial in respect to y, it's going to start off the same way. So it's going to be 1 over 1 plus, it's going to be y squared over x squared times. Now, when we take the derivative of y over x in respect to y, that's going to give us what?
1 over x.
1 over x. Okay, so I'm going to do a little bit more multiplication here and multiply by x over x here. So I can go ahead and get rid of the complex fraction that's going to happen. So if I multiply this out, I'm going to end up with x over x squared plus y squared. Okay. Any questions there? All right, so now we said that the partial in respect to x was equal to negative y over x squared plus y squared. So now what I want to do is the second order partial in the second order. I'm in the second order derivative in respect to x. Second order partial in respect to x. So if I do that, okay, that keeps in mind that y is going to be the constant, okay? So another way that I can look at this expression, the first order, is the same thing as saying negative y times x squared plus y squared to the negative 1, okay? And then make our life a little bit easier. All right, so if I take the derivative of this, it's going to end up being y times x squared plus y squared to the negative 2. Then we're going to take the derivative of the inside, which is going to be 2x. Okay. So if I clean this up, and again, I can write this as a fraction. So it's going to be 2xy, and it's going to be over x squared plus y squared squared. Any questions there? Okay, so we're going to do this kind of the similar approach in order to do the second order partial in respect to y. Okay, so again, we can write that the first order partial in respect to y, we can write that as y times x squared plus y squared. Excuse me, it's not going to be y times, it's going to be x times. So it's going to be x times x squared plus y squared to the negative 1. So if we do the second order partial in respect to y, it's going to end up being negative x times x squared plus y squared to the negative 2 times the derivative of the inside, which is going to be what? 2y. Okay, so we're going to end up with negative 2xy over x squared plus y squared quantity squared. Any questions? Okay, so now what we have left is the mixed order. So the mixed order, basically what I'm going to do, I'm just going to use this to help me do the mixed order. Okay, so if I do that, okay, so we said that s of y is equal to um, x times x squared plus y squared to the -1. So if I do s of x, y, so the mixed order partial in respect to y, then in respect to x. So if I want to take the derivative of this in respect to x, what rule do I have to use?
Product rule.
Yes, I got to use the product rule. So I'm going to do first times the derivative of second, which is going to be -1 times x squared plus y squared to the -2 times. Now, if I take the derivative of the inside in respect to x, I'm going to get what?
2x.
Okay. And then we're going to do plus. Then I'm going to do the second times the derivative of the first. So if I take the derivative of x in respect to x, that's going to be what?
1.
1. Okay. So basically what I'm going to do is to clean this up. So in order to clean this up, I'm going to factor first. So if I look to factor this, all right, I see that I have expressions raised to a power that I've got underlined. So when I factor, I want to factor out the smallest. So if I factor out the smallest, that's going to be the expression to the -2. So I'm going to have that x squared plus y squared to the -2 comes out. Okay. Now, when I pull it out of this first piece, that means this term is completely gone. So all I'm left with is x, -1, and 2x being multiplied together, which is going to give me -2x squared plus. Then from the second piece, when I factor this out, now again, keep in mind when you're factoring, it's basically the division rule for exponents. So when I factor out a -2, essentially what I'm doing is that I'm doing -1 minus a -2, which is going to give me this expression to the first power. So I'm going to be left with x squared plus y squared. Okay. So if I clean this up, okay, I'm going to be left with -x squared plus y squared, and this is going to be over x squared plus y squared squared. Okay. Any questions? All right. Are there any questions about partial derivatives? Okay. So for homework, you've got the partial derivative homework. Okay. And I think I've already got the answers in there and everything. So just basically, you really need to practice this. If you don't practice, then it's going to be kind of a snowball effect when we throw in chain rule. Okay. Also, quiz 7 is available. It's due Tuesday, not Thursday. Tuesday. Okay. It's through Tuesday. Any questions? All right. Well, that is it for today. Keep in mind that if you do have any questions, you can always email me. Don't forget about my office hours. Um, so just don't forget about that. Okay. You guys have a great rest of the day, and I will see you over on Tuesday. Have a great weekend.